Hello everyone, this is Wang from Central South University, China. Today I would like to talk about our work on high-performance adaptive video streaming using NDN WLAN Multicast. First, I would like to talk about the background for our research. Today, the video streaming is the hottest applications, from the video on demand, live video, video conference, to short video and online education. According to Cisco's VMI Global IP Traffic Forecast, by 2022, the video streaming traffic will take up to 71% of internet traffic. So, since video streaming is very hot and there are a lot of related work to improve users' QoE in video streaming, we can categorize them into three parts. The first is the adaptive bitrate algorithms, and the second is the network measurement, and the third is network protocol. In our work, we do not work on the ABR algorithm. We are working on the network protocol design to improve users' QoE in video streaming. Before going to the details, I would like to talk about the Scalable Video Coding, SVC. The traditional video coding is the AVC, which is the de facto standard for today's internet. Different from the AVC, the Scalable Video Coding, they encode the video into different layers representing different quality of video. So the consumer can measure the network bandwidth and the coordinate. They will adjust which layer they would like to request. So this is how it works for the scalable video coding. But in our arguments that due to different channel condition of different user in WLAN, traditional AVC cannot leverage multicast. We think SVC is a fit for NDN architecture because user with different channel condition, they can request the same lower layer video packet so that we can use the multicast to improve the performance. First, we would like to talk about the motivation and challenges for the video streaming in WLAN. So first is the low WLAN channel utilization due to massive interest package. From this picture, we can see before fetching a video, we have to get the MPD file, and then we will request the according segments and the according layers. So this brings two questions. First, sending more interest packets when you requesting high quality video. And the question two is due to the massive uplink interest competitions, they will have severe channel competitions. So we'll reduce the WLAN channel utilizations. The second channel motivations is the low efficiency of multicast transmission with basic data rates. Due to the traditional multicast, they will be sending, they do not have any reliability mechanisms, so they will be sending the basic data rate. So increasing the multicast transmission time and reduce the user's QoE. The basic rate multicast transmission cannot support the high performance requirements for the video streaming transmissions. Seeing this from these two graphs, we can see that when with different multicast bitrate, the multicast data rate, the video bitrate will increase when the multicast data rate is increased. So how to leverage multicast to improve the user's QoE? And the second question is how to leverage adaptive multicast data rate selection to improve the bitrate. So we would like to talk about our architecture and goals. So overview, our approach, we have two mechanisms. One is the AP-based interest proxy scheme, and the second is the layer-based multicast data rate selection scheme. We do not change, we didn't do any change to the producers. We make some modifications to the consumer and the access point, the WLAN access point. So our goal is to improve the overall users QoE by reducing the number of interest sending and mitigate to fierce competition of double LAN channel, and to improve the video transmission efficiencies by designing adaptive multicast data rate selection scheme. So we'd like to talk about our design. First, we'd like to talk about the AP-based interest proxy scheme. We'll talk about the interest registration in consumer side. First, we have a specific naming for the SVC package, which you use the base URL prefix and with /SVC and / the video name and / the total number of layer of the SVC and then / segments number and the layer number and the trunk number. The scheduler will adjust the interest registration size according to the adaptive bitrate algorithms. We send in the proxy interest to AP and then add the related interest to the pending interest table. So in the AP side, we add a registration table to record the base URL, MAC address, and the video layer, and the MAC sequence information from the interest registration package. So the interest proxy package forwarding process is showing in this graph. So the interest registration will go to the registration management, and they will be unboxing the interest registration package, and the AP will send the interest instead of representative of the consumer. And then also after sending the interest, they will record the naming record the related entries in the PIT. After data come back, they will do the data classification to see whether this data will be multicast or unicast. Then if the data will be multicast, they will detect the layers, and based on the layer number, they will select the proper data rate and send the data by multicast. So here we have a double LAN. In our previous work, we have designed an NDN WLAN Multicast mechanism. So the multicast is based on the consumer who are requesting the same content. So the NDN actually supports multicast. So we have a low cost for multicast group maintenance. And so we will not go into much details in the NDN WLAN multicast. If you're interested, you can refer to our previous works. So the second scheme is the layer-based multicast data rate selection scheme. So we use the scalable video coding, and we design it with using the NDN multicast to transfer the scalable video coding package. So we have a graph show that since we have different segments and different layers, we put the naming prefix. We map the naming prefix to different MAC address groups. So when the data package arrives, they will send using different MAC addresses. So the SVC layer detection, we use the SVC layer detection to do the data classifications. If the data is by unicast, So we use the traditional minstrel algorithms to do the data adaptations. If the data is multicast, we will connect the video layer information and decide what kind of data rate it will be used. For case 1, when the video layer is layer 0, that means this is the basic layer of the video. And that means everyone needs this kind of layer. So the AP will select the basic data rates supporting the physical layer of wireless card. So only the video data base layer is correctly decoded, and the other enhancement layer can further improve the video quality. So case 2, if the layer of video is larger than 1, is larger or equal to 1 and less than 3, the AP select the minimum data rates of this unicast, the multicast group, to transmit the multicast data, and the rate minimum is represented as follows. In the case 2, when the video layer is layer 3, the AP select the data rate, the greedy data rate, to transmit the multicast data, which maximizes the throughput in this group. So we do the ndnSIM simulations to see the performance of results. For the evaluation metrics, we use the video bitrate, the video layer ratio, and the stalling time, and the buffer level, and the startup time. And for comparison, we use the baseline method, which is basic rate selection, and the interest proxy with the basic rate selection. This is some settings for our simulations. First, we look into the video bitrate of different skin. We see from the figure 6, this is the box plot of video bitrate. Our skin increased 7 times bitrate of the ABC. And also we can see from the figure 6, the multicast data rate increased from 30% to 7% in our skin. Seen from figure 10, we show the average video bitrate in different number of stations. As we can see, as the number of stations increase, the video bitrate will decrease. But in our skin, even when the station number is 24, the bitrate is still above 4 megabits per second. When in the basic rate skin, the bitrate will less than 1 megabit when the station number is larger than 20. And also we can see from the figure 7 is the video layer compositions in different skins. In basic data rates, most of the layer is the layer 0. But in our skin, the layer 3 percentage is 20% when station number is 8. Even when the station number increased to 20, the layer 3 is still composed about 10% of all videos. Also, we can see from the stalling time, our skin is much better than the basic data rate skins. So also we evaluate if when we have some background traffic, how our skin will adapt to the dynamic network conditions. We have a background traffic appear from 50 seconds to 100 seconds. We can see that our skin is 6 times better than the basic rate skins. When the back traffic is over, so the bitrate will be returned to normal. So this is our evaluation part. For conclusion, to our efforts is to improve the overall user's QoE in video streaming. We designed HPNM to solve the challenges. The interest proxy skin can significantly reduce the number of interest packets sent in from consumers, which will reduce the WLAN uplink competitions. We designed a layer-based multicast data rate selection scheme to fine-grained select appropriate multicast rate for different video layers. And HPNM can benefit many video applications and potentially benefits the data-driven network protocol and application. For the future work, we will working on the adaptive bitrate algorithm for SBC, and we will also working on the multi-source, multi-path, which is the unique feature for NDN with SBC. So thanks for your listening, and that's all for my presentations.